Here's one more problem from the AP Level C exam. This is from the year 1990, problem number 3. And again, I'll give you time if you want to hit pause so you can print out your own copy and take notes alongside. You're welcome to. You can just resume as soon as you're ready. Okay, so welcome back. This problem is about a vertically mounted spring with two masses attached to it, and they're not glued or rigidly attached. They're just resting somewhat delicately on the top of the spring that has a stiffness of 1,000 newtons per meter. So we're asked, when the blocks are at rest, how much is the spring going to be compressed from its original length? So the two of them are allowed to gently be lowered down until the spring is compressed to a new equilibrium position. In other words, if this represents the spring in its relaxed state, and now this stress is added in the force of the weight of these masses, then how far below does it compress to? So the key being when the blocks are at rest. In other words, if you were to set these on and instead of gently lowering it down, if you place these blocks on top and then just quickly pulled your hand away, then they would go past an equilibrium point, the spring would get highly compressed, and the whole system would oscillate and bounce up and down. But eventually, if there's any damping, those oscillations are going to die out and the system's going to come to rest. So you can either put the blocks on, drop them suddenly, and wait for a long time until they settle to rest, or alternatively, place your hands along with the blocks and gently lower them yourselves until they come to this equilibrium position. So what's the value of delta y is basically the question here for part A. So this just comes from picturing a free body diagram. Once they do come to rest, then the force from the spring, the force pushing upward from the spring, matches the downward pull of gravity, and so this value of delta y, oh well, shame on me, k delta y. So k delta y is equal to mg. Delta y is equal to mg over k. So 8 times 9.8 divided by 1,000. And we get about 7.84 centimeters. Okay. So moving on, part B. The blocks are now pushed down and released so that they oscillate. So now that they've reached, here's the spring in its unstretched position. Here's the equilibrium position. We'll call this the natural length. And y equals 0, equilibrium position. And then they're lowered even farther, an additional delta y beyond that point, and that causes them to be set into motion. What's the frequency? Well, if it's an ideal spring, frequency is independent of amplitude and only depends on the value of mass and the spring stiffness. In fact, period is equal to 2 pi times the square root of m over k, so frequency is the inverse of that, 1 over 2 pi times the square root of k over m. So we get a frequency equal to 1 over 2 pi times the square root of 1,000 divided by a mass of 8. And we get a frequency of about 1.78 hertz. Okay, moving on to part C. Determine the magnitude of the maximum acceleration the blocks can attain and still remain in contact at all times. So depending on how far you initially displace, however far it's displaced downward from equilibrium, that's how far it's going to rise back up above the equilibrium point, and there's no problem while it's decompressing, and now the spring is launching back upward and becoming longer. Then there's going to be a force of contact, a normal force that's increased, pushing up on both surfaces of the blocks, and they'll stay stuck together. The problem happens when it reaches its highest point and starts to come back down. If the acceleration of the springs is greater than the acceleration due to gravity, then there's no force to keep everything together. So simply put, that's our answer for part C. The maximum acceleration would be equal to acceleration due to gravity. So part D, let's figure out how far could the spring have been compressed initially so that we don't exceed this acceleration. So right up to the limiting case, if the acceleration is equal to the maximum acceleration, which in turn is equal to g, well, we know that the force exerted by the spring is going to be maximum force exerted by the spring is k times the amplitude, and then at most that could equal mass multiplied by the max acceleration. And so the greatest compression we could have is this value of A. So A at most could be mass times max acceleration divided by k. So the greatest amplitude we can give it is 8 times 9.8 divided by 1,000, which is right back to our previous answer of 7.84 centimeters. So that kind of makes sense, right? Because if we were to push it down that far, then when it rises back up, it's going to return to its natural length. If we pushed it down any farther than that to begin with, then it's going to rise even higher than its natural length when it rebounds past the equilibrium position. But if it were to do that, once it turns around and comes back down, it'll have a greater acceleration than g. So no surprise that our answer to part A and our answer to part D have the same value. Part E, determine the maximum speed of the blocks if the spring is compressed that distance. So let's see. Find the value of maximum speed. Well, the maximum kinetic energy is equal to the maximum potential energy. So 1/2 m multiplied by maximum velocity squared is equal to 1/2 k times maximum displacement squared. We can cancel out the 1/2s, and v is equal to the square root of k over m multiplied by a. This gives us a value of the square root of 1,000 over 8 multiplied by 7.84 times 10 to the negative 2 meters. And this gives us a maximum velocity of about 0.88 meters per second. Okay, so there you have it, an example of a vertically mounted spring and applying the laws for simple harmonic motion.